Welcome to the 8th week of the machine learning course. It's a final week. It will be dedicated primarily to preparations for exam, but also to give some examples of applications to further illustrate what can be done with techniques from this area. So this is the first lecture, and we will here look at back at some assignment related tasks, and my purpose is to try to give you a picture of what your exam will look like. The general outline of the upcoming exam will be as follows. There will be in the order of 50 tasks. These tasks can give you 100 marks in total. On the actual exam, all tasks will be given in multiple choice type form. So this is what would it look like. So a disclaimer for now, for today, for this lecture, is I'm going to exemplify tasks here, but not using a multiple choice type. I do this because it's more compact, and the multiple choice time is pretty awkward when I just want to exemplify which kind of task you can wait for. So there will be, as for the assignments, like a balance between recall type tasks, which will only be worth 1 mark, but then there also will be problem-solving tasks, which are worth more, typically 2 to 3 marks. There will be a few more challenging tasks worth 5 marks. What I will focus on very much today is how these tasks will be spread over the course. So the idea is that the exam should cover most parts of the course. So I actually try to model the course now into 21 thematic categories covering the content. It's not necessarily so that in an exam all these categories will be represented. It could be so that there are more questions or tasks on one such sub-theme, or it could be so that there are no questions or tasks at all. So that will be up to the exam when you see it. Tasks will be well aligned. That's the ambition to the type you have seen at the assignments. They may not. They can be slightly different in style, but the aim is not to move too far from the tasks you have seen so far. Also, I want to ensure you that the tasks will be tightly coupled to the lectures. Of course, the recommended readings you should consider as useful, but the recommended readings are more to enhance your understandings of matters discussed on the lectures. So you do not have to fear tasks on topics only mentioned in the recommended materials, even though the recommended material can illuminate or explain better or deeper something mentioned on the lectures. So that's the general outline. Let's turn now to my proposed thematic categories. As you understand, this kind of pretty complex course can be structured in many ways. So there is no actually the right or wrong way of structuring a course. It's up to your taste, more or less. So here on this slide, you can see these 21 categories. At the top left, you can see very general topics like elements from basic mathematics and statistics, elements from logic and computer science, elements from theory improving, and artificial intelligence. I mean, these are not the primary topics for the course, but they will more or less always somehow come into play in the various corners of the rest of the course. So therefore, they are here, and therefore there will be a few elements on the exam that relates to that, but it's not a major part. So after that, the course continues and goes into the realm of learning scenarios, content about how categorization works, a few different approaches to inductive learning, maybe as slightly side topics, some material on Bayesian networks and genetic algorithms. They are part of the picture, but they are not super central, as you may have recognized for the course. Then we come to instance-based topic learning, which is an important topic with many connections, and that's followed up by cluster analysis as an example of supervised learning. From that, the course moves into learning scenarios where one can say that in one form and another, there are available domain knowledge that can be used as a strong basis for the learning process. And that is more or less ended with reinforcement learning, which is a natural starting point for moving into the realm of neural networks. And as you can see here, there are, I know you also, I guess you already realized from the material of week 6, there is a strong focus on neural networks. And the main reason for that is that is one of the sub areas of machine learning today where there is a lot of limelight on. And what you can on the next slide is just to illustrate how the flow of the course has moved, more or less, not exactly. It's a linearization, actually, of how I envision the course has developed, more or less following the path I just orally described. What I will do now is simply have a pretty fast walkthrough through these subtopics, or I would say content categories. There is absolutely no ambition here to present anything new. So if there happen to be a little detail that is new, it's more of an error rather than something that was aimed for. I merely tried to collect on each of these slides some keywords that would give you the right to listen to look when you want to recapitulate what was articulated and focused on in the earlier lectures in the course. So the first slide here is on mathematics and statistics. And as I hope you understood, vectors, matrices, and tensors. In general, a lot of mathematical subtopics, one can say related to some type of arrays, is important, and operations on those. They will occur over and over again within the course. Also some geometrical concepts relevant for visualizing state spaces, some optimization techniques occurring in particular in relation to reinforcement learning. Graphs occur pretty often. So the very basis of graph theory, properties of graphs is important. and also to some extent simple aspects of calculus as integration and differentiation. So these are the key mathematics topics needed. Um, some statistics is also touched, primarily inferential statistics, where we draw conclusions about the population from sample. I mean, the core is actually the mathematical basis, the probability theory, particular we touch stochastic processes, Bayesian methods, and Monte Carlo methods. So this is the picture for math. So very simple questions of recall and also very simple questions, problem solving character can occur for these topics. Let's move on to logic and computer science. As you understand, we will only scratch the surface here, but also elements from logic and computer science have occurred in the course. Central for learning are is the relation to the classical inference styles like deduction, induction, and abduction, and so on. That's the key part. With respect to computer science, which is an extremely wide area, of course, we mostly relate it to some basic knowledge about algorithms, data structures, and to some extent the databases. In the week 7, we also talked about supporting tools. So of course, we also have touched programming languages, tools for distributed computing, APIs, program libraries, technical computing systems. Then going on directly, I think, to artificial intelligence and theory improving. There are a lot of couplings between theory improving and artificial intelligence, and we have talked about that in various corners of the course. We also talked about knowledge representation schemes. So that's necessary. We cannot talk about learning if we don't talk about knowledge representation. And one particular scheme that was highlighted was logic programming. Also, search techniques occur in various corners of the course. So now we are moving more into machine learning. So as you remember, very early in the course, there was just some general lectures about the different types of learning scenarios. Whether we look at supervised learning with pre-sorted example or unsupervised learning, or the very specific situation of reinforcement learning, where the behavior of the system is evaluated and graded by some external environment. We also discussed distinctions like batch learning contra online learning, batch learning being roughly that you collect all the examples, all the instances, make the learning process based on them. So in principle, you have all the instances at hand at the same time, while online learning works more dynamically in a situation where new instances come up over time. Of course, important is the relation between classification and regression that also occurs systematically during the course. The relation between symbolic and sub-symbolic learning. The different two situations where we want to adapt the behavior of a system contra more of a data analysis scenario where we don't really have a system in a narrow sense. That's the behavior which is changing. And then a number of separate, more specific concepts, always important when we discuss the various algorithms like overfitting, underfitting, linear separability, etc. Also in the same part of the course, we talked about categorization, and categorization also being close to semantic networks, for the reason that many times in artificial intelligence, categories have been represented in terms of semantic networks. So what we did here was to look at basic principles for object-oriented descriptions, the description of objects in terms of features, and building up structures among categories, some interdisciplinary basis for how we do categorize our world, and finally a little more detailed information about the format of the so-called semantic networks and the relations modeled in terms of edges in the network. Okay, leaving that, we come, I would say, to the core of the machine learning course, the kind of classical core algorithms for doing induction, more or less without a pre-existing domain theory. So here we talk about the different kinds of languages that's needed to represent the instances and the hypothesis, how to define relations in the hypothesis space, typically in the form mathematically of a partial ordering, also distinguishing between different approaches to do this, either data-driven, starting from the examples, or by generate and test, which is essentially means the opposite. We start top-down, building up and test hypotheses and see how well they fit. So data-driven, bottom-up, generate and test, top-down. Then the focus of this was more on comparisons of various data-driven search strategies, like depth first, breadth first, and version space. Let's move on. After that, we looked on decision trees and how to build up decision trees, both for classification and regression. And the method is essentially top-down. So we talked about various properties of the relation between the instances and the built-up trees, such as purity, homogeneity. We spent some time on various information theoretic measures that can help us to guide us in how we build up the trees, and doing some calculations of the simple calculations on those. We also looked at this particular algorithm, which I would say is the mother algorithm in this realm, called ID3, and some simple examples of using that. Then we also touched, but not so much in detail, how we can handle various situations that can occur, like underfitting and overfitting, and especially overfitting, how to handle that by pruning of the tree. Finally, we looked at alternative approaches, how to build up parallel trees in parallel trees, and then choose the best tree or the average result by using all the trees together. One example called random forest, etc. So after decision trees, we went into Bayesian networks, and I would say what we did in Bayesian networks was not so merely to look at the learning of Bayesian networks, even if this is an area of itself, but rather the basic properties of these networks. And at the core there, we have the Bayes theorem, which helps us to infer causes from evidences. We also had as assignments simple calculations of based on the use of Bayes theory. Also, we looked at very, very small examples where we built this very small Bayesian network for a particular examples. And at the key of those exercises is the build-up of the conditional probability tables coupled to the network nodes. So this is the focus here. Let's move to the next. So genetic algorithms is an important area, but there have been many things covered on this course, and not everything can be treated equally thoroughly. So, of course, my judgment is we had a pretty shallow descriptions of genetic algorithms, focusing on the basic ideas, the way you need to represent things with a terminology inspired by genetics, and also looked at a typical algorithm scheme, including various phases, such selection of the best genes, evaluation of those, generation of creation of new generations, and so on. And finally, and there we also had some exercises coupled to that, very small exercises related to the key operations, in particular the crossover relation, which is the main operation for reproduction. Finally, we also shortly described how one can implement rule-based systems in terms of genetics, and thereby, by doing that, one get a learning property of the rule-based system. So you have a rule-based system, you can apply it, you can look how it works, you accumulate evidence, you use that evidence for evaluating the fitness of the rules in the sense how much did the rule contributed to a good outcome of the problem solving. And then you essentially create a new generation of a rule base where some of the rules are taken away, some of the rules are reproduced, some are changed, and you get a new generation, and then you can apply it again. And also, strangely enough, I think, which I also highlighted as a parallel, I mean, when we come to neural networks later, it's important to have a mechanism also to backpropagate the results or return given from the outside world, and essentially grade the performance of the various components. Neural network case, it's the performance of the various weights in the system, but in this case, with the classifier system implemented as a genetic algorithm, it's essentially becomes a grading of the specific rules, but one needs a similar backpropagating algorithm as in the neural network case, and here it's called the bucket brigade. So nothing is new under the sun. After that, we turn to instance-based learning, which is a lot of content in that section. So where we discussed instance-based learning in general, the structure of the instance space, we focus on the k-nearest neighbor algorithm, we look at distance similarity matrices, we also looked at the so-called weighted nearest neighbor algorithm, we then discussed binary linear classifiers, and we also went more in depth onto support vector machines. And finally, we discussed the situation where we could buy smart mappings from a two-dimensional space to a higher dimensional space, typically maybe three, could enable the use of support vector machines also for nonlinear cases. And as a natural extension of that, we went into cluster analysis. And I think a lot of the focus there were to looking at the large variety of different kinds of clustering techniques. And I think I would say we mostly look onto positioning-based clustering, where k-means clustering is the main approach. We looked at hierarchical-based clustering and also density-based clustering. There was some focus there we had some focus on the distance similarity metrics, which are more or less the same topic as for instance-based learning. Actually, we didn't do much calculation in this realm. There have been some examples of the assignments on how to calculate proximity matrices, and that should be distinguished from a similarity matrix. A similarity matrix concerns the distance between the instances, while the proximity matrix concerns the distance, quotation mark, between the clusters. After that, we went into the realm of learning in the context of prior knowledge. And there were two parts initially that are more closely related to the existence of theories in symbolic form. So one is inductive logic programming, and what we did here was to discuss both some logic programming fundamentals, but also basically the two main ways of doing learning in the top down in inductive logic programming. It's one based on specialization, the other based on generalizations, and we showed some examples on these two variants. After that, we went into explanation-based learning, which is essentially the situation where you have an almost complete domain knowledge or domain theory that you want to kind of complete or finalize. Also, explanation-based learning in many cases doesn't mean that totally new knowledge is created, but rather that the available knowledge is compiled in more efficient forms. The next big block is reinforcement learning. We talked about the terminology, we talked about the concept of value function, we talked about the most common way of modeling reinforcement learning situations, which is the Markov decision process model. And then we talked of various ways of attacking the solution to such problems. We talked about dynamic programming, we talked about Monte Carlo simulations, and finally time difference models with Q-learning as our main examples. And of course, we also discussed some more principled distinction between various approaches here, passive versus active, on policy versus off policy, and so on. So this became, I would say, a pretty substantial part. So even if it's just one sub-theme here, I would say, yeah, the general comment is there's not always a total balance between these parts. Some are much more context dense than others if we look at these, what I call here subtopics. Before we went into neural networks, we had a pretty short lecture on case-based reasoning. Obviously, this topic, which is an area of itself, has not been so well covered in the course either. But let's move now to, I would say, with the most heavy subtopic, set of subtopic here, so related to neural networks. So first, there was these lectures focused on the single atomic parts, the neurons, and of course the precursor to the current neural model called the perceptron. And of course, important at the core here are the weight updating scheme, as we will see for most of the artificial neural network approaches. There was also some talk about the kind of various kind of activation functions that can be used and the properties of those. After that comes, one could say, the classical core methodology part of artificial neural networks, which is the multi-layer networks where the neurons are the part, and the methodology for feeding forward signals through the network for estimating the error at the output level, and then for backpropagation of the outcome of that error estimation, and as a basis of the backpropagated error constituents, updating the weights. And a natural follow-up is then an extension of the basic ANN architectures, which are the recurrent neural networks, which is essentially a way to most cases artificially creating a possibility to handle states by introducing these special units that can be unfolded to handle the multiple states of a specific item in the model. So we discussed the kind of standard version of that. We call it vanilla recurrent neural network, but we of course illustrated how it can be extended with putting these elements in multiple layers, and also how there can be communication back and forth in the same layer. So where we really did look more in detail how this works were on the vanilla version and the unfolding of that. We also talked very shortly about short long-term memory, which is a very successful variant of these. Successful in the sense that it's been used with great success in certain applications areas. Then more or less, for a little while, we moved from the mainstream ANN into the realm of associative memory. Of course, also still modeling associative memory by an artificial neural network. And the focus there was mostly on the approach by Donald Hebb, as inspired by cognitive models of the brain. Then we moved on to further realizations of associative memory two versions of that, one called the Hopfield networks and another called the Boltzmann machine. So we discussed the Hopfield networks, we discussed the energy concepts that is used to guide us in the search for optimal solutions. And also, in the Boltzmann machine, we looked more in particular on the process called annealing, inspired from metallurgy, where you essentially heat up, that's an analogy, of course, heat up the system, and then slowly cool it down, with the hope that this heating and cooling should, in some cases, get out of undesirable local maxima and bring us to the global minima. So then, actually, the end of the core content of the course was focused on convolutional neural network. As you may remember, convolutional neural network is primarily targeting applications in image recognition. So we both looked a little about the source of inspiration for the basic operation here, convolution. We also looked at the interdisciplinary inspiration sources for this whole architecture, which is actually the special organization of the human vision system. So we looked at various terminologies and various items occurring in a convolutional neural network architecture, and we showed very, very simple examples how these central operations could be done, primarily convolution and pooling. So that's it. We reached the end of the sub-themes. So that was all the sub-themes. So what I've done now, and this I will not go through in detail actually, it's here for your service. It's here to just give you examples of the kind of questions that can come up on your exam relating. And it's very important to now, I want to stress that this is just inspirational examples to make you focus easier when you now go back and rehearse based on the material you have from the earlier lectures. So what you find actually here is a list of questions that I hopefully makes you can guide your preparation studies in the right way. There are many questions that can be put, obviously, with each little category. Also, the other disclaimer is that for space sake here, I didn't want to give this question in multiple choice form, but I want to stress that on your exam, all your tasks will be formulated in multiple choice form. They will not be open questions like here. But as you understand, every open question can be re-engineered into a multiple choice form, which happened on your exam. So please have a look and use this as a source of inspiration. It may be so that some of these questions have occurred in the assignment. It may be so that but mostly I don't think they have. But it could be so. So it's not that these are questions. Examples are exclusive. So these were the simple recall questions, 1 mark. And then you got a similar list of example questions with the same disclaimers for the more problem-solving oriented one, which give a couple of marks each, depending. The actual number may depend on the judged complexity of the small task. And finally, I also gave you some examples spread out across the sub-themes of the little more complex tasks that you will have. Not many, not so many as this. So I mean, if you want to give have the picture of the balance between tasks, go back to the first slide I gave you. So don't believe you will get 10 hard questions. This will not happen. You will get a handful or fewer of hard questions. Majority of the questions will be the Mark 1 and Mark 2 to 3 questions. Okay, so good luck with that. I hope this lecture has been useful for you and it can guide your preparation for the exam. So thanks for your attention. We will follow up with another lecture. However, I want to state very clearly that this lecture, application and demo example, is only there for your service. It has absolutely no bearing on the exam. So I advise you now to focus on the preparation for exam. And hopefully what I've given you today is useful. This very final lecture is just to give you some illustrations of the usefulness of the area and has, as I said, absolutely no bearing on your exam. Thank you so much.